Thank you, Eva. Good afternoon or good morning to everybody. And the subject of today is automated metros. It will be much technological, but with a deep effect on urban mobility and on its sustainability. The subject that I will deal with are at first the hourly capacity, because we have to understand where we are looking at in terms of passengers per hour per direction. The second is the automation levels, because we are speaking about automated metros and the GOA. Then the comparison with classic metros or conventional metros. And last but not least, linear motors and magnetic levitation. So at the end, I would like you to understand which is the role of automated metros and which kind of demand they can satisfy in urban context in particular, and why automated metros, or how far they can be sustainable. First of all, which is the goal? The goal is introducing automated metros in general, starting from the hourly capacity, as I said before, and then providing some comparison with conventional metros, and at the end, magnetic levitation. I recall a slide that I already used in the past, that is, innovative transport systems are based on the conventional three elements that are infrastructures, travelers, and vehicles. And the modern context of urban mobility and of transport in general is take a look at the energy, because we rely on certain kind of energy sources that we have already seen in the past. And in fact, a great part of literature devotes a great attention to efficient public transport, well-used vehicles, new solutions for engines and motors, electrification, and intelligent transport systems. And automated metros are within these efficient systems. We will discover it later. First of all, the hourly capacity. Typically, an automated metro starts where the urban roadways, of which we have spoken the last time, arrive at a limit. I mean, we've seen in the last seminar that with the urban automated people mover with cable traction or urban cableway, we can arrive up to 8,000–9,000 passengers per hour per direction, no more. Then, if we look at the conventional metros or undergrounds, typically they start from 20,000 passengers per hour per direction. Of course, if they can transport these quantities of passengers per hour, they can transport less. But from the economical point of view, they are not convenient anymore, because you cannot pay for their investment and their operation, typically. In between the conventional public transport, buses, tramways, automated people movers, monorails, which arrive at 8,000–9,000 passengers per hour per direction, and underneath the conventional or traditional undergrounds or metros, which starts from 20–25,000, we have automated metros. So we have typically a ground for the great part of European cities. 500,000, 1 million, 1.5 million inhabitants typically are bringing with them a flow which is in the order of 10,000, 15,000, 20,000 passengers per hour per direction in the mainstreams. So there is a typical area for automated metros. Okay, so having understood which is the hourly capacity that they can satisfy, let's take a look at the typical operational criteria that are used for analyzing both in general automated metros, but both automated metros, but in general other kinds of transport systems in the urban context. The frequency. Which is the frequency that I can guarantee? Of course, in automated metros, having not a driver, I can arrive to a very high frequency. Very high means one convoy each 80 seconds, 90 seconds, 2 minutes. that typically is not reachable with onboard drivers, because you would need a quantity of drivers and a reliability of their behavior. I mean, they have to start their operation in the exact moment when it is requested. Well, this is not necessary in automated metros because they are automated, of course. So the frequency can be high, and this is typically a criterion for attracting demand. Second, the commercial speed. Having not interaction with the normal network, and well, this of course regards also conventional metros, but having typically smaller vehicles with higher accelerations than the conventional metros, and being frequent, I reduce time at the stops. And this makes commercial speed, I remember that commercial speed is the distance divided by the time from the origin to destination. So including the stops, including the various times that you can encounter, that you can find during the path. The third element is the distance between stops. Well, typically an automated metros can have a distance a bit less than a conventional metro because the inertia is lower, being the vehicles a bit smaller typically, as we will see later. The regularity, this is very important because we typically have 99.98% of availability of the service that is very close to the regularity, and this attracts demand because the traveler, the person who has to take public transport, knows that with a very high probability, if he or she goes to the metro stops, will find a vehicle in a couple of minutes, 3 minutes, 4 minutes, whatever is the frequency. Safety. One of the first automated metros, probably the first one in Europe, is that of Lille in France, operating since 1986, and that's zero. Accidents, zero. I mean, not related to the system itself. Maybe some people hurting each other or whatever. And this means interest, very high interest in the safety of the system. And then the hourly capacity is what I said before, between 9, 10, and 20, 25,000 passengers per hour per direction. Very interesting for many cities. And then the service production capacity, that is the commercial speed multiplied by the hourly capacity, the productivity or the quality of resources used, the service utilization rate that is typically very high, and in the recent years, the energy consumption. Okay, the energy consumption is very similar to that of railways, a bit higher because we have higher accelerations and typically higher acceleration and deceleration phases because we serve urban context with a certain distance that we will see later among the distances, the stops. Then there are some other economic criteria, like economic financial indicators, investment per kilometer or per passengers to be transported in the year, per inhabitants, the efficiency indicator typical of an economical analysis, and the effectiveness of indicators. What I can tell here is that typically a conventional underground or conventional metro starts from, in Europe, 115, 120 billion euros per kilometer, even 150 or more. A cable-driven automatic people mover or urban cableway is around 10 million euros per kilometer. Sorry, I said before 110 million euros, sorry, not billion, million euros per kilometer. So I repeat, urban cableways, 10, 15, something like that, million euros per kilometer. A conventional metros starts from 115, 120, even 150 million euros per kilometer. And an automated metro is typically between 50, 60, 80, 90 million euros per kilometer. There is a certain amount of money that is necessary for the automation, that we will see later. And this implies the first investment to be high. Then once you have the control of the system that is installed with the maintenance area, of course, too, then if you extend that metro, of course, the euros, the millions of euros per kilometer are typically less. Okay, then this is just a resume of the hourly capacity that I said before. We are typically around 9 up to 20, 25. I wrote 30 because we are moving towards the mobile block, of which I will speak later. Okay, what do we have to organize, to define when we start designing an automated metro? We have typically three main columns. The operational time that is related to the performances of the vehicles that we want to use, acceleration, maximum speed, the dwell time with the discharge and take on passengers, the vehicle design, the ticketing system, though typically this is separated from the operation itself. So you enter into a station, you verify your ticket, and then you proceed, unless you are ticketless, but this is some more recent cases. Related to some more recent cases. And then you have the stopping time at the terminal and the terminal layout and the recovery time. These three columns define the commercial speed, the operational speed, from which you can calculate, sorry, today we have not the time, but this is a typical exercise, calculate the number of vehicles that you need according to the network that you have to cover, the frequency and the inputs that I've just listed. At the end, you are also able to calculate the energy consumption, and this can be done through instruments and also simulators that are typically used. Then, the fleet sizing is typically related to the demand to be satisfied, the service that I want to guarantee, typically in frequency in the automated metros, and then according to the route that you have to cover and the travel time that you have according to the performances of the vehicles, you arrive to the cycle time, and divided by the frequency of the service, you obtain the number of vehicles. Just resume the main concepts, then we can recall some aspects later. One main element that I mentioned before, sorry, I go back to let you see, that is related to the stopping time and the distances among the stops, is this. If you enlarge, if you extend the distance among the stops, then the time within the system will be lower, while the time to arrive to the system, so I have to walk, for example, or arrive with the car or by bicycle at the stop, typically increases. So the higher is the distance, the higher is the time as an average to reach the stop, of course. But once you are within the system, the higher is the distance, the less is the time within the system itself. So we have to, let's say, calculate in a certain way the sum of the two functions and define, according also to the performances of the system we are dealing with, which is the best distance that we can apply. Of course, we will not apply, we will not define a stop in any place, but we will try to match it with a commercial area, a station, a university, or whatever it is that is able to attract the demand. But the distances have to be calculated, as I said before. So, what is typically, as I introduced at in the first minutes, is typically associated to the automated metros is a high frequency and little vehicles. So this can be done only through a high automation. Okay, this is a main simple concept. But to guarantee a high automation, we need two preconditions. One is that the line has not to be accessible. Okay, so it has to be protected with double doors, and you can access the train only if it is at the stop. Otherwise, the line will not be accessible at all, and this is a precondition at all. Well, if there is some damage, of course, but normally it cannot be accessible. The second is that you need to control all the vehicles and the stations beside the line from a controlled area, so from a control room, where you have the possibility to monitor passengers, vehicles, infrastructures, and stations. Infrastructures in terms of lines and stations. Okay, so these are the two preconditions for an automated metro. Then, once you have these, we, let's say, get at a lower level and we see which are the technological requirements. The technological requirement, first of all, imply that you need to localize the vehicles, and not just with the block sections as in railways, but in a continuous way, as we will see later. And you need to know which is the actual speed, which is the distance among the vehicles, their exact position. How can you do that? This is a list of the overall technologies, more or less, that you can find in the world. They can be either with contact, more conventional, typically applied in the railway sector, like pressure train. Well, you pass with the axles, with the bogies, and you make a pressure, so you identify the passage of a vehicle, or with a contact of a metal part, or a wheel contact on the line, so it's written on the straight on the line. And this can be either mechanical or electrical. But the highest part of the highest percentage of undergrounds in the world typically are based on a non-contact, without contact identification of the vehicle, magnetic, electronic, with a screening effect, or an inductive connection. No matter what is the technology, you are able to identify in a discrete way where is the vehicle, but in a discrete way. So how can you know in a continuous way? You use the odometer. That means the little wheel that is applied on the axles of the automated metro, and so you can know second by second where is the metro. The problem of the odometer is that it accumulates errors, though very little in a contact of steel on steel, a bit more if you have rubber, but anyway, we have rigid rubbers in automated metros, so it still remains very low. But anyway, from time to time, you have to erase the errors. So once you calculate the distance covered with the odometer, you erase the error by availing yourself of these systems. That means when you arrive in a certain point, like a transponder or a beam interruption or a very high frequency signal, then you erase the error that is accumulated by the odometer. Okay, then once you know the position of the vehicles, you can apply a number of things that we will see later. Okay, the levels of automation starts from the manual driving that typically you have on tramways and on conventional metros, and you arrive to the full automation of the entire traffic system with unattended vehicles. And this passes through three levels of automation: ATP, ATC. Well, ATP and ATC are coupled together, so is the first one. ATO and ATS. So ATP, ATC imply that you are able to localize the vehicle and you have a punctual protection of the vehicle. Okay. Then ATO organizes the operation. So you can arrive at the stop, and then when the vehicle is at the stop, you can open the doors of the station beside those of the vehicle itself, and you can have the target brake. That means that you arrive in a certain point and the vehicle stops exactly there. That is not so easy with a person driving. And then you have the ATS, that is automatic train supervision, which is the supervision of all the lines or the line that you have under control, and you can insert a vehicle automatically and extract a vehicle from the line in case of damage, in case of any need. Okay, so ATP, ATC, which are coupled together, then ATO, and then ATS. These are the three main levels of automation. ATP, of course, implies the track status detection and a continuous control with the ATC of the vehicle speed and its position. The ATO is what I said before, the precision of target stopping at the station, the door closing and opening control only when the vehicle is there. If the vehicle, for example, with a very high mass on board, has a longer stopping distance, then you have to recover that error by aligning the vehicle with the doors. From time to time it happens. For example, I live in Turin and there is an automated metro since 2006, and from time to time it happens that the vehicle is a bit before or more probably as stopped after the target stopping point, and so we have to reset the position of the vehicle, typically some centimeters or many centimeters, something like that. Okay, the ATS as a control, as I said before, with a continuous and dynamic updating of the diagrams and dwell times, with a communication with the ATO, automatic train operation, and in case of need, you can establish a routing over alternative path if there are any problems, I would say. Okay. When you speak in the market, I would say, of automated metros, the constructors, the metro builders, typically speak about GOA, that are the grades of automation. Sometimes they speak about ATP, ATC, ATO, ATS that I mentioned before. More frequently, they speak about GOA. GOA 0, that is conventional systems, no automation. And then the levels of automation are GOA 1, GOA 2, GOA 3, and GOA 4. I haven't got much time to enter into detail, but what I want to say is that the GOA 4 is the maximum level of automation. It implies a certain amount of technology and of costs, investments. I just resumed these GOA levels here. You can see that in the GOA 4 you have trip setting, train stopping, operating and closing doors, emergency operations that are all automated. And you have an attendant in GOA 3 for opening and closing doors, assisting, and for emergency operations. Okay, with a driver in GOA 2 and GOA 1. Okay, just a little, so we have understood so far that we have a certain hourly capacity, that we have a certain level of automation, and the level of automation can be classified and implies two possible categories. Then let's make a little comparison with the light rail transit and the classic or conventional metro system. The conventional metro system has a maximum speed of 80, 100 kilometers per hour. 100 is already high. Why? Because notwithstanding you might have a distance between stops of 1.5 kilometers, well, you need to reach that speed. Otherwise, it would be a loss of speed that you have at disposal. The minimum radius is typically 150 meters. Consider that conventional rail systems start from 200, 250, 300 meters of minimum radius. And then you have an average distance between the stops of 500, 1000, but even more, as I said before, 100 and 200 meters, 1.5 kilometers, sorry, 1,200 meters, 1.5 kilometers, something like that, with a commercial speed around 30, 40 kilometers per hour. Light rail transit is a bit less, typically, with also lower minimum radii, and an average distance between the stops that is even lower, but with also a lower commercial speed. Here you can resume the typical area of automatic metros on the bottom left part of this graph, and the area of traditional metro systems, with a possible competitiveness area within the two systems. I have to say that around the world in the last 10 years, the great part of metros are automated. Here you can see some from, sorry, I wrote UNI, that is Italian standardization body, but EN is European normative. So it's just a translation of the European normative. So the data are the same all over Europe. And this normative establishes the rail-based metro and the rubber-tied metro, which kind of minimum deceleration, maximum instantaneous deceleration, and maximum jerk they have to satisfy, just to have an idea of those values. These values are anyway quite higher than those of conventional train systems. Okay, then what about distancing? So we have seen hourly capacity, automation. We have just seen the performances and the area of competitiveness, but which is the distancing? Okay, in a conventional rail system, typically we have a fixed block. That means that you split the line into block section, and each block section has to satisfy the braking space of the train which has the highest braking distance. Is it clear? So I take the train with the higher mass and the higher speed, or both of them, and I say, which is the stopping distance? Okay, that defines with a certain overlap, so a certain margin, a certain further amount of meters, the distance between the stops. And, sorry, the distance between the two block sections, so not stops, block sections. Sometimes the block section correspond to the stops, but it depends on the line. So the block section have a certain length on a conventional rail system, but in recent automated metro, I'm referring to the very last years, the block section is abandoned in favor of the moving block. In the moving block, the precondition is that you can localize, as we said before, the train that is before, and you calculate the position of the following train or the distance in terms of, or the headway, according to the position of the train before. And this is called mobile block. The mobile block or moving block, we have both the terms. Moving block represents a moving block, and mobile is just a mobile block. Okay, the mobile block implies the use of odometers, as I said before, and some balise or transponders along the line for erasing the error. And the operation is made this way. You see that you have the vehicle A, a BOA that is a balise or a transponder. Sorry, this is in Italian. And the following train B has to keep a distance according to the profile that the train before is following and according to the braking distance of the B train. Okay. Typically, we have trains or convoys of the same performances because we have homotactic operation. Okay, so this is what typically we have in very modern or very up-to-date automated metros. This is an example referred to Italy, to Milan. We had before, but also Turin in this moment is passing from the fixed block to the mobile or moving block, and we obtain, according to the operation before, a gain of 20, even 30% of hourly capacity. And this is the reason why you saw before even 30,000 passengers per hour per direction, because this is the case of moving block. Okay? So, is always convenient the moving block? It depends. It depends on the speed that you can raise, because once you increase the speed, you increase also the stopping distance. And if you increase the stopping distance, the moving block is not so, let's say, attracting anymore. You can see it here in the red, sorry, it's in Italian, mobile block, the red one. You increase capacity, trains per hour and passengers per hour per direction, once you increase the speed. But after more or less 90, 100 kilometers per hour of maximum speed, then you start decreasing the positive effects of mobile block. This is also in literature. And I've mentioned a publication when I uploaded some of the publications concerning this subject. Okay, then what about something more about classic or conventional metros? Well, in order to understand why going towards automated metros. Well, typically during the construction phase, in a conventional metro, you have to make an excavation, so you have to dig, you have to cut the pavement and go underneath the soil for tens of meters. I don't know if any of you already has gone to the Paris metro, conventional metro. Well, the lines which are at the deepest level arrive at 90, even nearly 100 meters underneath the soil. 90 meters. How much time do you imply? How much time is required to arrive there? 4 minutes, 5 minutes to arrive at the stop from the surface, from the street. And in an automated metro, no, not at all. Because since you have, as we will see shortly, much smaller sections, you don't need to go underneath the soil at very deep levels. Well, it's not so necessary, but typically you remain very close to the surface. How close? 18 meters, 20 meters, 25 meters. This means that, for example, I've tried many times with my watch to see how much time do I imply is required for starting from the street and arriving at the stop of the automatic metro. 20 seconds. 20 seconds. So this means that it's attractive because I can reach the vehicles in 0.2 of seconds. And differently from other cases. Then there is another issue, another effect, that when you have to excavate the stops at very deep levels, 30, 40, 50, 80, 90 meters, this costs a lot. And even to prepare the tunnel, if the diameter is larger, it costs more. So the automated metros cost less than the conventional one because they don't need to excavate the stops, while the tunnel is made with a tuning mooring machine with diameter of 7 meters, for example, 8 meters. So this is interesting. This is the comparison. On the right side, you have an a traditional metro where you have the pantograph and you see a diameter of 12 meters, 13 meters, something like that. You have a certain dimension of the trains, then the pantograph which requires a certain space. But on the left side, the red vehicles, they are of an automated metro. They don't have pantographs because they collect the electricity along the line on the bottom since the line is not accessible, so it's, let's say, it's important for the accessibility and to avoid how do you call it in English? Well, the possibility that a passenger touches something inside the line. So you don't have that because the line is not accessible. And you collect with brushes the electricity along the line. You avoid the pantograph. The vehicles are smaller because they are more frequent. And this implies a section of 8 meters, for example, or even 7 meters. So less expensive, and the dimension of the station is smaller with, as we said before, a depth that is quite smaller, lower than that of conventional metros or traditional metros. Okay? Then another aspect related to automated metro is related to the stability or instability of the rush hour. I represent it immediately. This is a conventional metro. You can have, sorry, it's in Italian, you can have a delay, you can have a supplementary time at the stop. During that time, more people arrive at the stop. This implies that the following convoy will require more time at that stop. Few seconds, doesn't matter, but these few seconds will sum up with the delay that was already present. And so it will transform the delay at the following stops into higher values. And this implies an instability. You will find 2, 3 convoys, one following the other, and then a certain time without convoys, say, well, this metro doesn't work. Okay. Differently, in an automated metro, since the engineer calculates the profile of the motion of the vehicle and also possible delays, because a person falling down while entering a metro can happen both in automated metro and in a conventional one. But in the automated metro, you can calculate the profile in order to recover this. And this is typically applied by the ATO and ATS that we mentioned before. So you can recover. You have not the typical instability that you are not able to recover in conventional metros. Okay? So, okay, I skip a couple of slides because I want to leave some time for the questions as usual. Then we have also in the urban context some tram-derived rail systems. Why should they be less or more attractive than automated metros? Well, it's evident. A tram-derived rail system, notwithstanding a certain level of automation that is typically applied recently, do not raise the capacity that has an automatic metro. Stops around 2,000–3,000 passengers per hour per direction. Okay. I skipped some slides because I want to arrive to another subject that is, well, this is related to the Vosges and the electric power. Well, typically we have continuous power, direct, and we supply, as I said before, the power with contacts underneath the line, well, on the bottom of the line. The Vosges can have either the motor, the electric motor on the axles, or you can have a transmission having the motors along the convoy. And now we will see in a couple of examples. Okay. This is an example taken from Lille and from Turin. Sorry, I use this because I live in Turin again. But this is a VAL. A VAL stands for Véhicule Automatique Léger. That means light vehicle, automatic light vehicle. Is not, well, is an underground with, as you can see here on the bottom, little vehicles, very frequent. The section of the tunnel is inside 6.4 meters. With 0.6 and 0.6 it arrives to 7.6 meters. And this is very small. And it's interesting because it doesn't cost much. Then here you can see the line. In this kind of automated metro, you have rubber wheels while the line is in metal, and you have the collection, as I said before, of the current, electric current along the line on the bottom of it. You can have it either in tunnel or in a viaduct. For example, in Lille, it starts outside the city in a viaduct. Then it goes down with the rubber tires. This is quite possible on the line, and it goes underneath the city where you have the city of Lille. Okay. In Turin, instead, it's all underneath the city in a tunnel. This is a typical vehicle. You can see, as I said before, you can have either the motor along the convoy here and then the transmission. You have a bar that identifies any obstacle, though you are not. Well, we are not supposed to have any obstacle because the line is not accessible, but just in case. Or you have the possibility to have the electric motor on the axle of the wheel, as you can see here. Then you have a wheel here on the bottom right of this figure, where you can have the direction, or where you can decide the direction of the vehicle, of course, under the supervision of the ATS. Okay, I just make some examples. This is Ansaldo. Now Ansaldo is not more Ansaldo, is Hitachi Ansaldo. I don't want to make advertisement to anybody, but just to have some examples. This is a scalable system, and typically, but it's similar to the previous one. So you don't have the driver, as you can see here, and you have a line where you have the stops, of course, according to what we said before. Okay, these are some examples. This on the right is the one in Turin, in the depot area, where they make maintenance too. The other one is in Lille. This is in Vancouver, that is called UTDC. The concept is similar, but it has a linear electric motor, of which I will speak later. These are other examples, even dated, some of them, sorry. Like Kawasaki in Japan, or the Westinghouse. They are similar, but recently a number of bids have been proposed around the world for providing cities with these automatic metros. I conclude with a few slides concerning magnetic levitation and linear motors. Okay, because so far I didn't say that, I gave it for known. All these automated metros typically have electric rotating motors. Okay, electric rotating motors. You have the power supply, you apply the, well, you provide a power supply and then you move with them. But An alternative is that of using linear motors, not rotating one. The principle is this. Sorry, again, I've got some slides in Italian, but you cut the stator and the rotor and you make them linear. And instead of having a rotating field with a certain, how do you call, delay in the rotating fields, the secondary one is following the primary one. Well, you have a translating field, but since you have not the self-equilibrium of a rotating electric motor, you have higher dispersions. I mean, a lower efficiency. And this is the typical concept of linear motors. You can have either the stator on board or the starter on the line, and these are two main differences. The starter on board means that you have to provide power to the vehicle once it moves. Okay, so once it moves, you have to provide electricity. The other possibility is to have the static motor on the line, so you provide power to the line, and the vehicle is following the line. What is the advantage? That you have not frictions, because you have an air cushion that is that of the electromagnetic suspension that we will see shortly. What are the cons, the negative aspects? So the pros is you avoid friction, but you have very high current, electric currents, which for the Joule effect imply great dispersions. So typically the energy consumption of these systems is quite higher than the correspondent, let's say, automated one with electric rotating motors. So why doing that? Well, with this we can reach, of course, very high speeds, but the record is not a problem of urban context. The record of magnetic levitation is 581 kilometers per hour, while for the high-speed trains is nearly the same, made in Paris, Strasbourg line with TGV in 2007. So this means that the speeds are more or less the same. Recently, not of course for urban application, there has been, well, in the recent years, the proposal for the Hyperloop, but this does not concern urban areas, of course. Okay, this is a graph of vertical forces of these linear induction motors, no gearbox, low mass, and you have to intervene, of course, on the voltage and a variable one, and the frequency of this voltage is also variable, at least at the startup, once you reach a certain speed. So you have a pulse width modulation, I don't want to enter into details, with a nominal voltage of 600 volts in direct current. Applications. Well, we have to distinguish, of course, both the linear induction motors and the LSM that are called synchronous linear motors. Sorry, synchronous linear motors, linear just once. And examples in Vancouver, in Japan, in maglev in UK. And then the LSM with the linear motor is in the Transrapid in Germany, the M-Bahn and the ADS. But some of these have been destroyed. I mean, destroyed. They did not survive. Why? Because they costed too much, and the safety conditions were too, let's say, unbearable. For example, the Transrapid was activated in, well, the banks decide, well, somebody convinced banks to fund the system in 1989, if I remember well. And then the system was developed in an experimental phase, and in 2011 the bankruptcy was declared. Well, it was interrupted. But also the one in Birmingham. Birmingham started with a system like that and then decided to stop it, and it was replaced by urban cableway because it was the first one too expensive. As regards the so we've seen that the traction is either with LIM or LSM. Sorry, I've been a bit fast, but LIM, linear induction motor, or LSM, synchronous linear motor. And then, as regards the suspension, we have again two possibilities. Electrodynamic suspension, EMS, like in the figure that you can see here. The vehicle is above a certain line, but in case the vehicle is too fast or the aerodynamic brings it outside the seat, the infrastructure, it flies away. So this is a problem. To avoid that, this solution has been proposed. That is the only alternative. That is the EMS, electromagnetic suspension. It's more, it's safer because the vehicle cannot go outside the line. But in case of lack of electricity, of any problem, it flies down, it lands on the line. And so you need some wheels in order to avoid that friction burns all. And this is the solution that you can see here. This is the line in Birmingham, already in 1984, the first applications, and it was dismantled in favor of urban cableway. And this was the M-Bahn, is the M-Bahn. I don't know what has happened to the M-Bahn in Berlin. Okay, a couple of minutes left for the Transrapid. That is the one that I mentioned before. There are applications of Transrapid. There is one in particular that is famous, that is that in Shanghai. Shanghai is a very huge city, and you have the connection between the city and the airport with a Transrapid system. But there you have a very high concentration of inhabitants, of demand, and the origin destination is fixed, because you have to go from the airport to the city and vice versa. So notwithstanding the high cost, you have a so high demand that you can pay it. So it's not only negative, that solution. When you have a very high concentrated demand, possibly it could be a good solution. Okay, and this is an example. The maglev is a similar one in terms of concept. It's an ADS. In the COVID period, the Japanese government decided to suspend the extension of this system. But you have already this Yamanashi test track from 2003, where the record in the world was reached, 581 kilometers per hour. No, of course, not for the cities. Okay, so I conclude, leaving a few minutes as we agreed in the past for the questions. That is, the hourly metro systems, the automated metro system have a hourly capacity that is very attractive, because it's typically between 8, 9 and 15, 20, even 25 or 30, but typically between 10 and 20,000 passengers per hour per direction. And this is what a great part of European cities need in terms of hourly capacity. Then we have seen the levels of automation and the GOA levels beside the ATO, ATP, ATC, ATP, ATO, ATS in the good order. Then we have seen some comparison with the conventional metros and with light metros. And at last, the magnetic levitation as an alternative wherever you can be satisfied. Okay, that's all. Sorry, I've been too fast, as usual, but I remain at disposal for any question.